Hey everyone, and welcome to today's Explainer. Today, we are absolutely tearing down the walls between theoretical, textbook learning and actual, gritty engineering discipline. We're going to be digging into an incredibly robust blueprint put together by Hardik Maru, and this isn't just some toy project. We're talking about a fully automated, production-shaped AWS web tier architecture. It features an application load balancer expertly distributing traffic across an auto-scaling group spanning two entirely different availability zones. But honestly, the absolute best part? There are zero manual console clicks involved here. In this entire setup, running Terraform apply is literally the one and only way this infrastructure comes into existence.
Okay, let's dive into this because Hardik hits the nail right on the head here. He says most tutorials stop at a single main.tf with everything hard-coded. This one is built the way I'd actually want to hand it to a team. And man, isn't that the painful reality for so many of us? You follow a tutorial, it works perfectly in a vacuum, but the very second you try to port it into a collaborative, real-world production environment, it just completely falls apart. This blueprint we're looking at today is engineered from the ground up to fix exactly that problem.
So here is our roadmap for the Explainer today. First, we'll go beyond the basic tutorial. Second, we'll see this modular architecture in action. Third, we'll navigate through multiple AWS environments. Fourth, we're diving into observability and system health. And finally, we'll unpack the deliberate infrastructure design decisions that pull this whole thing together.
All right, Section 1, Beyond the Basic Tutorial. Let's talk about breaking out of that vacuum and look at the core differences between a simple learning exercise and true, battle-tested infrastructure as code.
Think about the stark contrast between how we practice and how we actually work. In the vacuum, which is where most tutorials just kind of leave you stranded, everything is hard-coded into one giant fragile file. You're relying on manual console clicks and maybe a quick Terraform validate if you're lucky. But in the real world, Hardik's setup is a totally different beast. It gives us highly reusable modules. It was actually documented before it was even coded, and get this, cost modeled before deployment. But the real game changer is that it utilizes remote state right out of the gate. Your Terraform state lives safely in an encrypted S3 bucket, completely protected by DynamoDB locking, so multiple teammates can deploy at the exact same time without blowing up the entire infrastructure. Onboarding a new teammate becomes a total non-event rather than some massive, terrifying migration.
Moving on to Section 2, Modular Architecture in Action. Let's see how this solution is actually built using distinct, highly functional building blocks.
You see, this infrastructure is absolutely not a spaghetti bowl of code. It's cleanly split into four independent and highly reusable Terraform modules. First up, you have a custom VPC. There are no lazy defaults here. Every single CIDR block and route table is a completely deliberate choice. Second, the security groups are built on a strict least privilege design. The instances only accept traffic directly from the application load balancer. They never talk to the open internet. Third is the ALB itself, designed for high availability across multiple zones. And fourth, the auto-scaling group, which also spans two availability zones. Composing a thin environment root out of these independent modules is just a brilliant way to keep your codebase incredibly clean and manageable.
Let's zero in on that auto-scaling group for a second. Instead of using complex, step-scaling policies with custom-built alarms, which, let's be real, nobody actually enjoys managing, this project utilizes target tracking scaling. This means it just relies on native AWS primitives to track your CPU utilization. AWS handles the entire alarm lifecycle for you behind the scenes. On top of that, the system uses ELB health checks to drive automatic instance replacement. If an instance suddenly goes down, the load balancer spots it instantly, and the auto-scaling group replaces it without you lifting a finger.
All right, Section 3, Navigating Multiple Environments. This is where things get really cool, showing how the architecture handles promoting code with actual purpose. Now, what's really interesting about this slide is how promoting across environments isn't just about spinning up more servers. It fundamentally shifts both the security and the cost posture. In your dev environment, you're running T3.micro instances in public subnets just to stay firmly tucked inside the AWS free tier. But the moment you promote to staging and prod, the whole architecture hardens. Your instances are moved into private subnets, sitting safely behind a NAT gateway. The web application firewall kicks on, and your instances get beefed up to T3.smalls. Plus, every single environment gets its own isolated state file.
And to juggle all these environments safely, there is some serious engineering discipline applied to the CI/CD pipeline using GitHub Actions. Every single pull request triggers a strict battery of offline mock tests,
And it planned tests against a live account. But the absolute best part? It uses OIDC, OpenID Connect, to assume an IAM role. That means 0 long-lived AWS keys are required anywhere in your setup. Literally none. It completely saves you from that dreaded 3 a.m. panic attack over a leaked key on GitHub. And of course, applying to staging and production is deliberately gated behind manual approvals. Which brings us to Section 4, Observability and System Health. Because if your system is going to break, you absolutely never want to be breaking in the dark. The magic number we are looking for here is 4. For every single environment, this infrastructure automatically provisions exactly 4 critical CloudWatch alarms, and they are wired straight to an SNS topic that pings your team's email. These 4 alarms just completely cut through the noise to tell you exactly what you actually need to know. Alarm 1, do we have unhealthy hosts? 2, are there 0 healthy hosts, meaning a total system outage? 3, are we seeing an elevated 5x error rate from the load balancer? And 4, is there a degraded response time that's actually affecting users? And to back all of this up, your ALB access logs land safely in an S3 bucket, and VPC flow logs are piped right into CloudWatch. It is literally production-grade visibility right out of the box. But here's a question. How do you know this scaling actually works? Well, this blueprint doesn't just guess. It includes a rigorous post-deploy testing methodology using a tool called K6. You deploy a real environment, you point the K6 load test script directly at the load balancer, and you actively force the CPU past that 60% threshold. You can literally sit there and watch the native scaling policy trigger in real time. It completely proves that your infrastructure can handle a massive traffic spike when it actually happens in the wild. Finally, we have Section 5, Deliberate Infrastructure Design Decisions. Let's unpack the why behind the code and look at the pragmatic trade-offs being made here. So the crucial point is how this architecture handles getting into your instances. There is absolutely 0 SSH allowed. None. Instead, it leverages AWS SSM Session Manager. This is just a massive security win. It means there are no SSH key pairs to generate, no keys to rotate, and absolutely no keys to accidentally leak. Plus, port 22 isn't open anywhere on the firewall. Your access is governed entirely, 100%, by AWS IAM roles. Another incredibly smart decision here is the pragmatic approach to cost discipline. When you move to those private subnets in staging and production, you have to have a NAT gateway so instances can reach the internet for updates, right? Well, standard AWS best practices usually scream, put a NAT gateway in every single availability zone. But NAT gateways are expensive. So this architecture explicitly chooses to use just one shared NAT gateway across the private subnets. It literally cuts those NAT costs in half. Now, the trade-off is that it becomes a single point of failure, sure, but only for outbound traffic. Your inbound customer traffic is still flowing beautifully through the highly available multi-AZ load balancer. It's just a smart, deliberate business decision baked right into the code. Which brings us to our final thought for today's explainer. I want you to think about your own projects for a second. Look at your team's infrastructure. If you deleted your entire AWS web tier today, could a single Terraform apply bring the whole shebang back perfectly? Well, with Hardik Maru's blueprint, the answer is a definitive yes. It really challenges us to reflect on the true resilience and automation of our own setups. I highly encourage you to take these deliberate, modular practices and start weaving them into your own work. Thank you so much for joining me today, and keep exploring.